The notation for the Laplace transform is L of little f of t gives us big F of s. If we want to go the other way, we have to get L inverse of big F of s. That will give us little f of t. Let's take an example. Suppose we want L inverse of s over s squared plus 4. Well, we go to the table of transforms and look at the right hand side for a function of the form s over s squared plus a constant. And here it is here. The constant in our case is actually 4, so a squared is equal to 4, which means that a is the square root of 4, which is 2. So this a is 2. So we see the answer is cos 2t times u of t. Now it would be a mistake to write down cos 2t by itself without the u of t, because cos 2t is defined, of course, for negative values of t, but we just want cos 2 of t for positive values of t, so that's why we multiply by the unit step function. So when we're going backwards, we really should write down u of t to emphasize that we just want cos of 2t for positive t. If we're going forwards, of course, we can leave out the u of t because we're integrating from 0 to infinity anyway, so it doesn't really matter. We're still going to get this. Here's another example, L inverse of 3 over s squared. Now we can actually take the 3 outside. Turns out that L inverse is linear. 3 is just a constant multiple of 1 over s squared. So we need to look up something in the table of the form 1 over s squared. We actually go to this line here in the table, and to get s squared in the denominator we need n to equal 1. So we get 1 factorial over s to the power of 1 plus 1. Well, that's our s squared, so n has to equal 1 for this situation, so we get t to the power of 1. Of course we have the constant multiple on top, which is 3. So the inverse transform of 1 over s squared is t, and then we multiply by the 3. And it's easy to run it forward. If we get L of 3t, since L is linear, we know L to be linear, that's just 3 times L of t. That's 3 times 1 over s squared. So since the Laplace transform operator is linear, since L is linear, then L minus 1 has to be linear. So in general we can write it like this: C1 and C2 are any constants, f of s and g of s are any two functions of s. Now in this example we want to get L inverse of 2 over s to the power of 4. Well, this is the form that it has if we let n equal 3. So here I've written down the statement using L inverse. So this is what we saw on the right hand side of the table, and this is its corresponding f of t, little f of t. So if we let n equal 3, in this here we get 3 factorial over s to the power of 3 plus 1. So that's that. Its inverse transform is t to the power of 3, where 3 is n. So how do we get inverse transform of 2 over s to the power of 4? Well, that's where the linearity property can be used. So we can take out the 2, and we can adjust things so that we can put a 3 factorial up here, but then we have to compensate by dividing by 3 factorial. So I'll change this 1 into a 3 factorial, and I'll divide by 3 factorial. So these cancel each other out, and we're back to 2 over s to the power of 4. Now, because L inverse is linear, we can take out this constant multiple 1 over 3 factorial. So we get 2 over 3 factorial L inverse of 3 factorial over s to the power of 4. And we know from the table that that's t to the power of 3 u of t. Well, of course we must multiply by the 2 over 3 factorial. L of 3 factorial over s to the 4 is t to the 3 u of t. Now let's look at L inverse of 6 over s squared plus 4. 6 over s squared plus 4 has this form here, although we have to do some adjusting because we want the constant a squared, whatever this number is, to be the square of the number on top, and that's not the case. So I've just copied out that result from the table. I'm writing it like this: L inverse of a over s squared plus a squared is sine of at. So we're looking at this thing here. Now, if a squared is 4, then a has to be the square root of 4, which is 2. But we've got a 6 on top here. So we've got to adjust this. So let's look at 6 over s squared plus 4. And we want to write it as 2 over s squared plus 4. Because then 2 over s squared plus 4 has the form a over s squared plus a squared, with a equal to 2. And then we can apply this rule here. So how do we convert 6 over s squared plus 4 into 2 over s squared plus 4? Well, we want to compensate for this 2, so we have to divide by 2 to cancel the 2. And we want to get a 6 on top, so we have to write 6 here. Make sure these are equal, of course. So now to get the inverse transform of 6 over 2, which is 3 times 2 over s squared plus 4, we can use the linearity property. We can take the 3 out, so it's just 3 times the inverse transform of 2 over s squared plus 4. And then we look up our table. A is 2, so we get 3 sine 2t times u of t. So we can put these two together for our answer. We can simplify this term a little bit actually. 3 factorial is 3 multiplied by 2 multiplied by 1, so we can cancel the 2's to get 1/3 here. Now in this example we have a function that is not in the table of transforms that we've seen. However, we can write this function as 2 fractions. So initially it's 1 fraction. We can write it as a combination of its 2 partial fractions. And we get 2 functions that do appear in the table actually. We've 1 over s minus 1 can be looked up, and 1 over s plus 2 can be looked up. So let's just recap on partial fractions. So there are actually 2 numbers which we can call a and b that make this work. So a and b are just constants. So what we do is we just add these 2 partial fractions together by getting a common denominator. We just multiply the 2 denominators together. We divide this denominator into the common denominator. We get the other denominator, s plus 2, which we multiply by the numerator a. So essentially we multiply s plus 2 by a. Then we divide s minus 1 into the common denominator to get s plus 2, which we multiply by b. Actually that should be s minus 1. So we multiply s plus 2 by a and s minus 1 times b. And we've now written these 2 fractions as a single fraction, and of course these 2 are equal. The denominators are already equal, as you can see, so the numerators must be equal. So 1 must equal this numerator here. So equating the numerators, we get this identity. Now this is true for all s. That's what an identity is. It's more than an equation. An equation might only be true for some values of the variable. An identity is true for all values of the variable s. We can gather the s terms together. We have a times s plus b times s here. Then gather the non-s terms together. That's 2a minus 1b. And on the right hand side we have 0 s terms, and with the constant term is 1. So the only way that both sides can equal here for all values of s is if the coefficient of s is the same on both sides. So we want this to be an identity. It's got to hold for all values of s. So we must have that a plus b equals 0. So it doesn't matter what s is. If a plus b is 0, then this identity will be true. And what's left then, 2a minus b, must equal plus 1. So we have 2 equations and 2 unknowns. If we simply add both sides, we get 3a equals 1. So we found that a is a third, as we saw. And if a is a third, then b must be minus a third, because a plus b is 0. So to go back here, we fill in for a is a third, b is minus a third, so we have a third over s minus 1 plus minus a third over s plus 2. We can use the linearity property of the inverse Laplace transform to get L inverse of each of these. This 1/3 can be taken outside, so we're just getting L inverse of 1 over s minus 1. So we go up here, it's got the form 1 over s plus a, where a is minus 1. So that's going to give us e to the power of minus 1t. That's e to the power of plus 1t. So that's that first term. Over here then, we can take out this 1/3, and we want inverse Laplace transform of 1 over s plus 2. Well, that's got the form 1 over s plus a, where a is 2, so we get e to the minus 2t. So that gives us the second term. Now the u of t has been left out of this, of course, but you can put it in if you like. Both of these are multiplied by u of t. Now let's look at this example. Notice that in the denominator we have a quadratic expression in s. We are going to write this single fraction as two fractions, one of them with a denominator that is linear in s, that is s to the power of 1, and the other fraction has a denominator that is quadratic in s, that is s squared. Now in this situation, if you're looking for partial fractions, the numerator for this fraction will be just a constant, which I can call a. It's just a number. However, the numerator for this second fraction is linear in s, so you better call it bs plus c. So b and c have to be determined. So we add these together to get our single fraction. So that involves multiplying a by s squared plus 1 and s minus 1 by bs plus c. And of course the numerators have to be the same, so 3 must equal everything up here. So multiplying out all of this and breaking it up into s squared term, s term, and the constant, we get this here. So we have an as squared and we have bs times s, that gives us a bs squared. As for the s term, well, we have bs times minus 1, so that's that here, and then we have c times s, that's this term. The constant term then is a times 1, and we have a c times minus 1, so we get a minus c. And this must all equal 3. 3 can be written as 0s squared plus 0s plus 3. So we have an identity. This has to be true for all s, so the only way that can happen is if the coefficients of like terms are the same. So we must have that a plus b equals 0. We must also have that the coefficients of s are the same. So we must have that c minus b equals 0. And finally then the constant term on both sides. The constant terms on both sides must be the same. A minus c must equal 3. So we can just add these two together and the b's will cancel. We get a plus c equals 0 plus 0. And if I write the other one in underneath it, a minus c equals 3. We get 2a equals 3, from which we get a equals 3 over 2. If a is 3 over 2, it means that c is minus 3 over 2, because a plus c gives us 0. Also, since a plus b is 0, and since a is 3 over 2, b must be minus 3 over 2. So we plug those values then in for a, b and c, and we get this here. That minus sign can be taken in here, of course. That's what we have here. So we want to get the inverse transform of this thing here. So we use the linearity property to take out the 3 halves here. So we have inverse transform of 1 over s minus 1 for this term. Use the linearity property here, and I'll take out the minus 3 halves. Take the minus 3 halves out of the top. And we have L inverse of s minus 1 over s squared plus 1. Now we can write this as two fractions, because in this form. This form does not appear in the table actually. This one does appear in the table. So I can write this as L inverse of S over S squared plus 1 minus 1 over S squared plus 1, and I can take L inverse into that. And the minus 3 halves is multiplied by both of these. So I've just written this fraction as two fractions. I've taken S over S squared plus 1 and then minus 1 over S squared plus 1, because these two are tabulated. So let's look up L inverse of 1 over S minus 1. Well, here it is here, 1 over S plus A, but we let A equal minus 1, so we get e to the minus 1 times t. That's e to the plus t. Next we want L inverse of S over S squared plus 1. So that's got to form S over S squared plus A squared with A equal to 1. 1 squared is 1, so we get cos of t. Now, L inverse of 1 over S squared plus 1 has this form here with A equal to 1. If A is 1, we get 1 over S squared plus 1. So that's sine of 1 times t. I need to make a slight correction here. I took minus 3 halves out of the numerator up here, so this should be S plus 1. So this becomes a plus sign, and we have a plus sign here. And if we multiply minus 3 halves in here and factor out the minus 3 halves, we get our solution, and then we can put the ut after it.